Welcome back to a course on complex analysis. Now we are going to see a result, that is chain rule. We'll start. It is given that function is analytic at a point z0, okay, which is parameterized using some variable t. At the point t0 it is evaluated, right? So generally what we have is z of we have z equals x plus iota times of y, and here we have parametrized. So z of t is going to be x of t plus iota times of y of t, and at a particular point t naught in the interval a b, we are evaluating the function z. Okay, we are not actually evaluating the function, we are evaluating the complex variable z. Okay, so this becomes x of t naught plus iota times of y of t naught. Okay, now we have the function w of t, which is a function of z. So if you differentiate this w with respect to t, what happens? This is what we have to prove here. So in order to prove this, we'll have to make use of the ideologies. Okay, so first of all, let me write f of z as u of xy plus iota times of v of xy. This is our usual notations, right? And as I said, these are the considerations that we have to make in order to complete this x of t plus iota times of y of t. So this is there. So now what happens is that your w of t becomes u of x of t comma y of t plus iota times of v of x of t comma y of t. Okay. Now we'll have to apply the chain rule for two variable case. Okay. Here both u of x of t, y of t and v of x of t, y of t are functions of two variables. Hence, by the chain rule for several variables, what we can write? So du upon dt, that may be written as del u upon del x multiplied with dx upon dt. You can notice this u is a function of two variables and x is a function of only one variable, plus del u upon del y multiplied with dy upon dt, and dv upon dt is del v upon del x multiplied with dx upon dt plus del v upon del y multiplied with dy upon dt. So this is the derivative. So first of all, find the derivative of du upon dt and dv upon dt. Substitute these values into, just let me mark this as equation 1. If you plug in the values of this into that, you would get what is required for you. Okay, now if we just directly substitute these values into it, we would get, that is dw upon dt is going to be what? Del u upon del x. So you can see what would happen here, right? So now what am I going to do is that I am going to combine the values, that is del u upon del x plus iota times of del v upon del x multiplied with dx dt plus del u upon del y plus iota times of del v upon del y multiplied with dy upon dt. Okay, just a minute. Yes, this is one combination. I must not do this way. I need a iota term that I need the iota term to come outside. So we'll have to do that way. Just a minute. Why? Because you can see the problem here. We'll have to get z prime of t outside. Okay, remember that. So keeping that in mind, okay, let me do the substitution directly. Dy upon dt plus iota times of del v upon del x dx upon dt plus again iota times of del v upon del y dy upon dt. Okay, we can make use of the CR equations, and we'll have to do some calculations, right? So from which what can we write? We must, okay, as we did. Okay, by CR equation, what can we write? Ux is equal to Vy and Vx is equal to minus Uy. So if you do this calculation, try to make everything in terms of U. Okay. So our dw upon, just a minute, dw upon dt becomes del u upon del x dx dt plus del u upon del y dy upon dt plus iota times of this Vx may be written as minus del u upon del y to dx upon dt. So we have this iota here, and here what may plus iota times of del u upon del x dy upon dt. So now what can we do? So this is dw upon dt is what, del u upon del x. Okay, let us combine the terms del u upon del x together. So it is dx upon dt plus iota times of dy upon dt. Next, if you see, we can do what? Plus del u upon del y. So it is dy upon dt minus iota times of dx upon dt. So if you try to take this iota outside from this, you would get okay. So here for simplicity purpose, let me write this as simply ux. So this is x prime plus iota y prime, and here I am taking iota outside. So when I take iota outside, this is uy. Here I would have iota, right? And this iota comes out. Let me take. So as of now, I am just taking iota outside. So I'll have to introduce minus iota square here. So I am taking iota outside. I can take minus also outside. So this becomes minus iuy, and this becomes x prime plus iota y prime. So from the now this x prime plus iota y prime may be written as z prime, and you may very well see that ux minus iota uy and x prime plus iota y prime. Okay, are we done? Or did we leave anything here? Okay, go through this once again, and I think we are almost done. So this quantity may be x prime plus iota y prime, that is, this can be written as z prime. okay, z prime of t, and we'll have just to say this is f prime of z. So just check with the sufficient condition for differentiability. So if it matches with the requirement, then we are done. If not, I think we have made some calculation mistake somewhere. In between that, we'll have to check. Just a minute. I'm working on it. I think we'll have to check only one thing. Did we leave any minus? So here everything went well. Here we have this x may be written as minus this quantity. Yes, of course. So here we did not have anything. So plus 1 has to be written this way. Minus 1 is minus iota is taken outside. So this is where. So by sufficient condition, we write this as ux. This minus uy may be written as vx, right? Ux plus iota times of vx multiplied with z prime of t. So exactly this is what this is our f of z. So with this, okay, I don't know whether if I write here it will be visible to you people. So let me make an arrow. Okay. With this, actually, we concluded ux plus iota times of ex is nothing but f prime of z, and we have the z prime of t, and this is what we were required to prove. So next, we are going to talk about the concept of antiderivatives. So before getting into the concept of antiderivatives, let me give you an introduction kind of a thing. We have seen that integral over any contour of a complex valued function. This may be written as integral c1 from z2 to f of z dz, and sometimes it is independent of the path joining these 2 points. Whether from this point to this point, whether we are evaluating in this contour or whether we are evaluating in this contour or whether we are evaluating in this contour. This doesn't matter to us. Okay, so the value depends only on the endpoints. In few cases, we have seen several examples already. In few cases, over a closed contour, the value turned to be 0 sometimes. Okay, mostly that happened, but sometimes it was not the case. Why it is so? There comes the concepts of antiderivatives and the piecewise continuity of the function, the direction. All these things are important in those contexts, right? So if you are able to, for any given continuous function f of z, if you are able to identify some function big f of z such that the derivative of this big f of z is small f of z, okay, this big f of z is called as the antiderivative of f of z. So what is it? Okay, what is the unique characterization of this big f of z? So this existence is unique up to the addition of constant. So this means what? If you are able to identify some function f of z which is an antiderivative of the given function small f of z, and you get some other antiderivative, let me say your big f of z and g of z are antiderivatives of small f of z. Let us consider this way. Then your small f of z minus, sorry, big f of z minus big g of z is constant. The derivative of this part is of course 0. So that is the speciality about this, and that is what I meant by saying this existence is unique up to the addition of constants. Here we have a theorem that tells us that the function is continuous in a specific domain D. Okay, then if any one of the following statement is true, then so are the others. Here they are not giving any guarantee that for every function which is continuous in a domain, the existence of antiderivative is true. They are not saying that way. If the existence of antiderivative is true in that case, then the other two statements will be true. That is what they meant. Okay, if this happens, then the other two will happen. Okay, as of now we are not going to prove this theorem. We just go through what is given in the theorem and we'll work out few problems, then we'll come back to the proof of the theorem, right? Okay, you may see very well here, function has an antiderivative throughout D. If the function is continuous, then the function will have antiderivative. Okay, that is what they are saying. So if it has an antiderivative, then what happens? The integrals of the function along contours which lie entirely in D. So you may consider this to be your domain. Okay, if you have a contour from, it may be a closed contour, an arc of this sort, a contour of this sort. This may be the case. These are some possible cases. Okay, the one thing that you must have is that the contour must lie entirely inside the domain D. Okay, which extends from any point to any point. Then your integral value depends only on the end points. Okay, so you'll have to substitute the end points in the antiderivative that you got in the previous thing. Okay, and of course the integrals over any closed contour is going to be 0. Okay, now let us get into the problems. The first problem that we have is we are asked to find out the integral value from 0 to 1 plus iota times of this thing. So it is evident that the antiderivative of z squared is z cube upon 3. Okay, so hence your f of z is z cube upon 3. This may be added with some constant. Okay, so whether I include this constant or not, that is not going to get bothered here, as I am about to evaluate the integrals over a closed thing. Okay, over the given limits. Okay, let me proceed with the addition of constants itself. 0 plus 1 plus iota. So when I substitute these things, 1 plus iota whole cube upon 3 plus c minus 0 cube upon 3 minus c. So this gets cancelled and I am left with only this quantity. So when I take it inside, actually this is 1 upon 3 times of 1 plus iota whole cube, 1 upon 3, 1 plus 3 iota minus, sorry, actually plus iota squared plus iota cube. So when you calculate this quantity, this is 1 plus 3 iota minus 3 minus iota. So this becomes 1 upon 3 times of minus 2 plus 2 iota. Okay, you can take this 2 outside, so this becomes 2 upon 3 minus 1 plus iota. This is the integral value. Okay, I have not specified what is the constant c here. It is just the constant of integration as we had in the integration and differentiation of calculus. Okay, it here this constant means a complex constant. It can be anything. Okay, here we have not bothered what constant we are adding to it. Just because when we integrate over a certain limits, those constants gets cancelled, right? So even if you proceed with only z cube upon 3 as an antiderivative, you are going to get the same value. Whether you add some constant, you can add some specific constant. It is up to you, right? I have done with the general ideology here. Now we'll move to the next problem. So this is example 2. So if you see the function that we are about to consider is f of c equals 1 upon c square. We know this function is continuous everywhere except at the origin, and this has the antiderivative. Okay, we cannot say the antiderivative. This has an antiderivative. Big F of z is minus 1 upon z in the domain absolute of z, which is bigger than 0. Okay, so this domain absolute of z bigger than 0, this domain is what? This is the which is the entire plane with origin deleted. With origin deleted. Okay, next consequently what we are going to do is that integral over c f of c dz is what? Is going to be 0. Okay, how did we achieve it? Let us see. First of all, let me say when the c is the positively oriented circle, z equals to e to the power iota times of theta, where theta lies from minus pi to pi. Okay, about the origin. So if we have to do the integration, how did we do? We just parameterize things and do the calculations, all other things. So we know the antiderivative is minus 1 upon z. So let me write it as minus 1 upon z. Now we cannot directly do the calculations, right? So if we have to evaluate over c, we'll have to parameterize things. Okay, how are we going to parameterize the things? Over c is the thing that we have to do. For the parameterization, we'll substitute z is equal to 2 e to the power iota times of theta, right? So minus 1 upon 2 e to the power iota times of theta. Now only the theta changes from minus pi to pi. Okay. So if you notice very well and do the calculation, what are you going to get? So minus 1 upon 2, you can take it outside, e to the power minus iota times of theta minus pi to pi. So what? You just do the calculation and see you are getting it to be 0. But in the statement itself, they have very well told you that if f of z is continuous, and if it has an antiderivative in a specific domain, okay, then this will imply the other two things happens. Since it has an antiderivative, we can directly say that the value of the interval around any closed contour which lies entirely in D will have the value 0. Okay, so here without doing these calculations, okay, you don't have to do these calculations. You can directly say the value is 0 just because, okay, by the theorem. Okay, by the theorem what we said here, uh, C lies entirely in the domain, this domain. Now you may ask me, so except this point, we have all of the points of the plane which is contained in the domain, and the contour that we considered is something of this sort. Okay, so if you consider this is our alpha, okay, positively oriented, so this is the point 2y and this is with radius 2, so that you people know for sure, right? So if you see only this point is deleted, the contour means we are tracking only the arc, we are not going to consider the interiors of the, here remember we are considering the circle not the disk, right? So now if you consider the function 1 upon z, okay, here the function 1 upon z cannot be integrated in the same way. Why so? Just keep thinking about it. Let us meet in the next lecture. Thank you.